Hi, welcome to episode number 3 of the Zero Pages. In this episode, we're going to be talking about assembly language. What is assembly language? Is it difficult to use? Why do we use assembly language? And how does it relate to programming for the NES? Before we can get into any of that, we have to understand a little bit about the hardware architecture of the NES. Along with a number of other components, the NES is built using a MOS 6502-based CPU called the 2A03, which was manufactured by Ricoh. It's an 8-bit processor that runs at 1.79 MHz. But what do I mean when I say CPU? I mean, we've all heard the terminology before, CPU or Central Processing Unit, but what does that actually mean in the context of writing a game for the NES? More specifically, what does that mean in the context of programming an assembly language? As the name implies, it is the central processing unit of the system. It is in charge of coordinating between devices as it runs software. In the case of the NES, it is the central unit that runs the game, but then talks to other components of the system like the PPU or the APU for graphics and sound. This means when you're writing assembly language, you're writing code for that 6502-based processor. But then, what does that actually mean? What is code? How does the CPU understand how to run the code that you've written for your game? And if all the CPU does is execute code, how do we make graphics appear and sound playback? The 6502 has a number of instructions that allow it to carry out simple operations. Those operations are encoded in memory as sequences of numeric binary data. When a CPU is executing code, what it's doing is it's reading the numeric sequence of binary data from memory and looking up what those numeric values mean in order to carry out the instructions that were requested by the user who wrote the program. And so that's what code is. Code and assembly language code specifically is instructions written in a text-based format that's easy to read for humans, that's later turned into that numerical sequence of instructions that the CPU understands how to execute. And unlike other platforms, where you might be writing code in C or C++ or some other higher level language, when you're writing 6502 assembly language, there's no operating system, there's no driver layer, there's nothing insulating you from the hardware. You're writing code that's going to execute directly on the 6502, and therefore you have to understand exactly how it works. The major benefit of this is speed. When you're writing your 6502 directly, without a compiler or an operating system getting in the way, it's very easy to understand what's going on and to get the most performance out of the 6502, which is important because it's not a very fast processor, especially by today's standards. This might sound daunting, but 6502 is actually a generally pretty simple assembly language. Now, I said simple, I didn't say easy. There's a difference because while the instructions themselves are very simple and generally simple to understand, the process of taking hundreds of assembly instructions and turning them into something like a game like Super Mario Bros. Is not simple. And this is why you'll get people who want to avoid assembly language. On its surface, it seems very complex or very hard. But if you break it down, it's actually very straightforward. It's just a matter of having the patience to learn how to put together the very simple assembly instructions into more complex code. In fact, what you'll find is once you get familiar with assembly language, the assembly part isn't hard. It's actually programming for the NES that's challenging because of the technical limitations of the system. So let's look at how you actually write 6502 assembly and contrast that with how you'd write code in higher level languages on other platforms. In other programming languages or other platforms, you're not generally directly accessing memory. In fact, many programming languages that are in use these days consider direct access to memory to be something that's undesirable or dangerous. Now, there are a lot of reasons for that, but to contrast that with the 6502, when you're writing assembly code on the 6502, The only way you have access to memory is directly, and you have direct access to the full 2 kilobytes of RAM that are available to the NES. Just like on other development platforms, you'll use the memory to store information about the game. Things like, what items is the player carrying? How many hit points do they have? What are the members of the party? What's their score? Etc. Let's look at some code that might appear at the beginning of your game, starting with a high-level version of the code and then looking at the assembly language equivalent. When your game starts up for the first time, the RAM on the NES essentially contains garbage. It's random data that hasn't been initialized with anything meaningful. And so most games, when they start, set all the RAM to the value 0. So if we looked at some code in C that were to try and initialize the 2 kilobytes of memory that we have on the NES, we can imagine where we have a buffer that points to that RAM, and we loop through from 0 to 2048, and we set the value to 0. That seems pretty simple. Let's take a look at how we do that in assembly language. Holy shit, what is this? Okay, it's not really as bad as it looks like, but there's a lot to unpack here, so let's start from the beginning. The first thing you see there is clear mem with a colon. What is that? That's called a label. A label is just a location in your assembly code that you can refer to later if you want to go back to that position in your code for some reason. We'll explain why that's there once we make it through the rest of the code. The next line has LDA pound $00 or load A with the value of 0. Okay, load A with 0, but what's A? So the 6502 has built into it special memory. In fact, all CPUs have memory built into them for use with certain operations. These special memory locations are called registers, and all CPUs have them: the 6502, the x86, the ARM series of processors. And registers are a very small amount of memory that's directly on the CPU that's super fast. But because it's on the CPU and because it's so fast, it's very expensive, so most processors generally don't have a lot of registers. In the case of the 6502, the 3 main registers that you work with regularly are A, the accumulator, X, and Y. The A register is named that way as the accumulator because when you perform mathematical operations, the results accumulate in the A register. For example, if you add 2 numbers or you subtract 2 numbers, the results of that mathematical operation end up in A. X and Y are called index registers, and they're called index registers because their function is to index through memory. Sometimes you need to operate on memory at a specific location, but other times you need to start at a beginning location in memory and then iterate over the memory starting from that location to some end location. X and Y allow you to do that without having to hard code memory locations into your code. Essentially, they're a flexible way of moving through memory to either read or write data. This is similar to how you would use an integer to index through a buffer in memory in C or some other language. The only difference here is that you're dealing with specialized hardware that allows you to do that. And so, unlike other languages where you have an unlimited number of indexes that you can create through just creating new variables, here you're limited to the 2 X and Y. So now that we know what registers are, at least at a high level, and there are some other registers I haven't talked about yet, which we'll get to in a minute, you can see that we're loading A with the value of 0. Now, that in and of itself doesn't really do a lot, but the next line that we have is STA, or store A, and then we have $ with a bunch of zeros after it, at comma, X. So store A does exactly what it sounds like. It's an operation that stores whatever the current value of A is into a memory location. Now, because we're trying to initialize all the memory in the 2K of RAM to 0, we could technically write store A0, store A1, store A2, so on. However, that obviously would become very cumbersome because we would have to do that 2048 times in order to initialize the full 2K of memory for the CPU of the NES. If you've done any other programming, or you were paying attention to the previous example that I had in C, you would immediately realize that this is a perfect example of where you would want to use something like a loop and an index. And that's what the purpose of using X is here. Part of the code that I didn't show yet is that I have initialized X to the value 0. And so that comma X after the store A 0000 is the index into the memory that we're initializing, starting at 0 and going from 0 to 255. The reason it's 255 is because the base address of 0 is added to the value of X at that current time, and that's the address that you're actually storing into. So if X was equal to 5 and the base address is 0, then we're storing into address 5. The other reason that it's 255 is because X, Y, and A are all 8-bit registers, meaning that they can only represent values from 0 to 255. And so you can see that each line that follows stores the value of 0 into an area of memory, starting with 0 indexed by X, and then the next line starting with 100 indexed by X, and that's 100 hex. Then the next line is 200 hex indexed by X, 300 hex indexed by X, and so on until we get to 700 hex indexed by X. And when that's done, we've got the full 2K of memory initialized. Now again, remember that X is an 8-bit register, which means that we can't go farther than 255 when indexing past the base address. And so we have to divide up the stores into different base addresses, 0, 100, 200, etc., in order to ensure that we initialize the full 2K of memory. Otherwise, after 255, X goes back to 0 and we would be missing some of the memory that we need to initialize. After we've gotten through all of the store operations, we have an operation INX, which means increment X. Now, that's really straightforward, and all it does is it just adds 1 right to X. The next operation is CPX, or compare X, with the value 0 after it. Now, this is a little counterintuitive because you'd think, well, don't we want to compare it to 255? Well, while we do want to count up 256 times, that doesn't mean that we want to stop at 255. What we actually want to stop at is after X rolls over to the value 0, because only then will we have initialized all 256 positions off the base address. And so we're comparing X to the value of 0. The next line, BNE, is branch if not equal. Branch meaning go to the position in code, and the following part there is the name of the label that we created at the beginning of the code. And so what we're writing here is branch to this label if the comparison says that the two values aren't equal. So if X isn't equal to 0, then branch back to the initial label for clearing the memory. And so we're going to do that 256 times. As we clear the memory, we're going to jump back. And then once X rolls over back to the value of 0, this branch if not equal won't branch anymore. And so we'll go past this branch instruction and continue on into the rest of our game code. Let's take a look at a few other instructions. For example, let's add two numbers together. Let's load A with the value 5, and then we're going to call CLC, or clear carry, and we'll talk about what that does in a second. And then after, we're going to use ADC, or add with carry, with the value 5. That will result in the value of 10 being stored in the accumulator. Carry, which was referenced before in the clear carry operation, is actually one of 6 register flags that are stored in the P, or processor status register. These flags have a value of 0 or 1, indicating that they're set or not. In the case of carry, this is used frequently when doing mathematical operations. In adding two numbers together, if the resulting value is larger than 255, the A register can't properly represent that value because it's only 8 bits. However, by checking the status of the carry flag, you can determine whether or not the result of that operation was larger than 255 and carry out your logic accordingly, including doing things like 16 and 24-bit mathematics. Conversely, you can see when doing a subtraction, you have to set the carry using SEC, and then you call subtract with carry SBC with the number that you want to subtract from A. If the carry bit is clear after the subtraction, then the value that you subtracted from A was actually larger than the value that was in A itself. The resulting value in A will be the result of the subtraction, but this is useful because it allows you to do things like determine greater than and less than relationships between numbers. Now, I can't cover all the operations that are available in the 6502 instruction set, but I'll leave a link below in the description to a really good reference for all the 6502 opcodes that are available. In addition to the instructions, it provides a little description of how the instructions work and what their cycle timings are, meaning how long it takes the CPU to execute the instruction, 2 cycles, 3 cycles, 6 cycles, depending on which version of the operation you're executing, because some operations have different variants. Some operate really quickly when operating on A directly and work more slowly when operating on memory. In general, operations on memory are going to be much slower than operations that take place solely on the CPU in a register. Additionally, I'll leave a link to a website that lets you execute 6502 code from a web browser, so you can do things like test out how addition and subtraction behave on the 6502 without having to do it within the confines of an NES program. I've found this website to be extremely useful because it helped me test out ideas and concepts without having to worry about the game getting in the way. We're going to wrap up this episode by talking a little bit about how the CPU communicates with the PPU and the APU for graphics and sound. I'm not going to cover everything here because those are going to be topics for other Zero Pages episodes, but I want to touch upon it a little bit now that we have a little understanding of how assembly language works. The 6502 doesn't contain any instructions specifically for drawing or playing sound on the NES. This wasn't an oversight, this was actually done on purpose because the 6502 was a general purpose processor built for a number of computers. The makers of the chip wanted the CPU to be used in as many devices as possible, and so it was designed to be flexible and used in a number of different hardware architectures. The 6502 was designed to address 64K of RAM. However, that didn't mean that it had to have 64K of RAM attached to it. In the case of the NES, we know that it only has 2 kilobytes of RAM. What the engineers at Nintendo did was they attached the 2K of RAM to the 6502 and then used the additional connections that would have normally been used to address the larger amounts of memory to the PPU and the APU using a technique called memory mapping. And essentially what that means is that you talk to the PPU or the APU by loading in from or storing into an address, just like you would with RAM. The main difference between addressing RAM and addressing a device like the PPU is the address range that's used. For the PPU and the APU, there are specific address ranges that have different meanings depending on the device you're talking about. For example, if I want to turn off all drawing on the NES, I can load A with the value 0 and store A into the address 2001 hex. While this looks like I'm writing to the address 2001, what I'm actually doing is writing to a specialized hardware register for the PPU and telling it to turn off all drawing functions. Like I said, I'll go into more about how the PPU and the APU work in future episodes of the Zero Pages, but hopefully this gives you a clear understanding of the basics of how to write assembly code and how to talk to devices on the NES. And before I go, one last thing I'll post in the description below is a link to the Nerdy Nights tutorials written by Brian Parker, or Bunny Boy, who created the Retro USB AVS. These tutorials are still one of the best sources of information for learning how to program for the NES, and should serve as a way more detailed supplement to the materials that I present here in these videos. As always, if you have any comments or questions, feel free to reach out to me on Twitter at Clervis. I'm also on Nintendo Age as Zelius, and you can also add a comment to the video down below. If you have more questions or you'd like to learn more about NES programming, you should definitely come check out my live stream, which I host Monday and Thursday at 9 p.m. Eastern, where I'm working on an NES game live on Twitch. I hope to see you there. Thanks for watching.